Okay, so now we're going to get into reactions involving carbonyls. We're going to start with reactions that make carbonyls. Now, the typical approach to making carbonyls is oxidizing alcohols. So, how to synthesize, and we're going to, again, focus on aldehydes and ketones to start. So we don't want to look at like carboxylic acids and that sort of thing right away. So to answer this question, how do we synthesize aldehydes and ketones? We're going to focus on oxidizing alcohols. Okay, now with that in mind, let's break down what a typical alcohol oxidation reaction looks like. Well, if you recall, oxidation can be the removal of electrons, addition of oxygen atoms, but also the removal of hydrogen atoms. And that's what we're seeing here. We're going to remove these two hydrogens, what we call the hydroxyl hydrogen, the OH hydrogen, and the carbonyl hydrogen. That is the carbon directly attached to the alcohol. So both of those hydrogens are going to be removed. I'm going to have like a generic reaction with an O in brackets to indicate an oxidation process to give rise to, in this case, a ketone. The same thing could be done with an aldehyde, where we have two hydrogens drawn, and we get something like this, which is equivalent to my preferred approach to drawing aldehydes with that aldehyde CH actually written. Okay. Actually, we've talked about these types of reactions before in Organic Chemistry 1, with reactions involving chromium reagents. So we have our chromium-based reagents, which are helpful to review, at least briefly. So here we have an alcohol. We're going to mix this with a combination of Na2Cr2O7. Maybe you remember this. You're like, wow, that's a lot of elements, but the one that I want you to focus on is the chromium atom at the center of it all, plus a little bit of sulfuric acid. In combination, these two things give rise to the Jones oxidation reaction, and they allow for the formation of ketones from secondary alcohols. Also, if you remember from Organic 1, there are some issues with the chromium-based oxidants, and that is, first of all, tertiary alcohols like tert-butanol can't undergo oxidation. Okay, we're going to get no reaction here because if you look at the structure of the ketone you want to draw, you break the octet rule. So the octet rule would be violated in the structure, so you actually see no reaction with tertiary alcohols. But then there's that issue with primary alcohols. So primary alcohols and the Jones reagent. And the Jones reagent, again, is H2Cr2O7, or the combination of the sodium salt plus H2SO4. So primary alcohols in the Jones reagent, which is this, lead to over-oxidation. And it's not really the primary alcohols that are undergoing over-oxidation. It's the aldehydes that result from them if you do an oxidation. Okay, so let's look at a primary alcohol here. A primary alcohol is one in which the carbon atom attached to the OH has only one thing attached to it. In this case, it's just a CH3 hanging off of that carbon with the alcohol. So we're primary. If we do a Jones oxidation, we could do the alcohol oxidation to the carbonyl, but in this case, we get an aldehyde. And aldehydes keep reacting in the Jones oxidation conditions to give rise to carboxylic acids. So it's the aldehyde intermediate that actually undergoes over-oxidation. It's not the primary alcohol itself. So you do overoxidation to make a carboxylic acid. This isn't a great reaction to do, even if you want a carboxylic acid. It's not super clean, and carboxylic acids are difficult to isolate from this reaction mixture. So you typically want something else if you want to go from an aldehyde to a carboxylic acid. So alternatively, we could use a different chromium-based reagent that is PCC. Now, it turns out that PCC is a CR oxidant without water. Right, so if you have PCC and you have a primary alcohol or a secondary alcohol, whoop, not that, the alcohol, you could do the oxidation reaction on either of these to get the aldehyde or the ketone. So both of those are viable products. You won't see overoxidation if you start with a primary alcohol, which is helpful. Now, here's the issue, though. These things are really bad for the environment. Just oxidations in general are really rough on the environment, really on the universe. It's really hard to do an alcohol oxidation. So instead of these chromium-based reagents, and I'm just going to emphasize that here. So chromium-based reagents are bad for you and bad for the environment, like in a big way. These things are very important in industrial chemistry, making carbonyl compounds from alcohols. And we used to rely greatly on chromium-based reagents because they're so reliable in terms of making the bonds that we want to make. In this case, I guess, breaking the H bonds that we want to break. But they're just so bad for us in the environment that we gave up on them to move towards other reliable approaches that are more environmentally friendly. And so here we have some alternatives. And they include the Swern and Des-Martin oxidations. So these are a combination of like protocols, use common reagents, and then an uncommon reagent that has a very simple protocol. So the Swern oxidation has a complicated protocol. I mean, it's not too bad. Protocol where you take your alcohol that you're planning on oxidizing. It could be primary or secondary, never tertiary. Those just don't undergo oxidation, as we went about earlier. We're going to do 3 steps. In the first step, we're going to add DMSO and oxalyl chloride. In the second step, we're actually going to add our alcohol. So our alcohol is this thing right here. So we have this pre-step before we have, I'm going to move the word protocol. Oh. Well, that didn't go well. So I took the L's with me. Okay, protocol. So we have this pre-step with DMSO and oxalyl chloride. Then we add the alcohol. Then we add triethylamine, which is 3 ethyl groups on a nitrogen atom. All of that to give rise to the carbonyl. Again, a lot of work. It's kind of cumbersome. You have to cool things down to like dry ice temperatures and that sort of thing, and add things in sequential order. It's a lot to just remove 2 hydrogen atoms, but this is an important yet difficult transformation to accomplish. And the Swern reaction is highly reliable. It's been known for years. It doesn't have any chromium-based reagents, so in that respect, it's better for us. It's better for the environment. It does release some dimethyl sulfide that kind of stinks, but in low quantities, it's fine. Okay, I mean, it smells bad. That's not. It's just not too much of a health issue in smaller quantities. Okay, so Des-Martin oxidation uses a periodinane reagent. It's a really funky reagent that's called a hypervalent iodine reagent because the iodine has a lot of things attached to it. So here, what we're doing is we have a simple protocol where we just mix our alcohol with this hypervalent iodine reagent. 1, 2, 3, 4. There we go. 5-membered ring on the iodine. The iodine's actually got 3 acetic acids attached to it. Okay, so that's the Des-Martin reagent. And so that will accomplish the reaction. Okay, so these are 2 prominent reactions. They're much more environmentally friendly. It's important to note that as important as these reactions are, neither of these better reactions is catalytic. And so people are spending a lot of time and effort still figuring out ways to do catalytic alcohol oxidations to carbonyls. You can rely on enzymes, but enzymes themselves are catalytic, but they don't have catalytic cofactors. And these are the molecules that are required to kind of tug off the hydrogens to make the molecule. But nature uses so many enzymes to actually accomplish alcohol oxidation. For example, when somebody consumes ethanol, that ethanol molecule, which is toxic, causes a little bit of delirium, a little bit of euphoria, that sort of thing. Everybody's having a good time. That needs to be dealt with because it is a poison. And so the body uses an enzyme to oxidize it to formaldehyde. You kind of wish, if the body could handle it, you kind of wish it would just use like a Jones reagent, because that formaldehyde sits around for a while. Excuse me, not formaldehyde, acetaldehyde. That acetaldehyde sits around for a while in the body, and it's kind of more slowly oxidized to acetic acid, not formic acid. Jeepers, that's that'd be an issue. Acetic acid's not really a big deal. That's vinegar. We can deal with that, especially in dilute aqueous solutions. But so the ethanol goes and it's oxidized once to the corresponding aldehyde, which if you look at the nomenclature video, that 2-carbon aldehyde would be acetaldehyde, which is then oxidized a second time by a separate enzyme to get to acetic acid, again, from last time. But the first step's very quickly. We can get the ethanol dealt with very quickly. The problem is acetaldehydes, while we're waiting for it to be oxidized to something that's pretty safe and actually kind of healthy to have floating around, the acetaldehyde is causing like headaches, nausea that's not induced by alcohol poisoning necessarily, light sensitivity, dehydration, diarrhea. That molecule in itself is the hangover molecule. And the problem is we don't have a rapid way of dealing with it compared to how rapid our ethanol is metabolized. So if we could get it to acetic acid's kind of nice. It does some helpful things in low quantities, and it's readily excreted through urine. So anyway, a little bit of a kind of a relationship to real life. Now, what about the mechanisms for these things? Let's go back to the notes just quickly. No mechanism here for the Des-Martin periodinane oxidation, but for the Swern oxidation, we're going to have the mechanism in the next lecture. Okay, so the next lecture we'll touch on the mechanism for the Swern oxidation because we're going to get our tuition dollars worth in terms of curly arrows for that one. Okay. Anyway, so until then, we'll see you next time.